Alright, let's get started. So, just a couple quick things on the quiz. I won't go over too much since the average was pretty high, 8.7. But I will point out a couple brief mistakes that I saw a lot when grading. So, I'm going to focus mainly on the first one because that's where I saw the most mistakes. So, when you do the substitution x cubed minus 10, okay, everyone, like most people figure that one out, no problem, so we won't go into that. But we translate everything into u and du. So I think some of the common mistakes I saw were applying the correct derivative rule, or the antiderivative rule, rather. So you just apply the antiderivative power rule. And then one of the other common mistakes I saw was making sure to translate back into x. So just keep that in mind while you're doing these types of things. And also, please do not forget plus c. So there's one thing to keep in mind when you're doing these types of problems. So, other than that, that's about it. So, anything else? Okay. All right, then let's introduce a brand new topic: integration by parts. So, or before I do that, quiz 3 is going to be next Wednesday. So next lecture, covering lessons 2 and 3. And exam 1 will be next Monday at 8 p.m., covering lessons R through 5. So lesson R, 1A, 1B, 2, 3, 4, and 5. So 7 lessons, so won't be too bad. Most of them are U substitutions, so yeah, let's go ahead and get started. So for the integration by substitution technique we've been seeing for the past 4 lessons, as you have seen, it's basically just backwards chaining. So in that sense, we can say that the substitution rule stems from chaining. Okay? But integration by parts is going to be based off of another derivative rule that we saw in Calc 1, except in this case, it's going to be the product rule. So integration by parts is from the product rule. So to see what I mean by this, let's go ahead and recall the product rule for derivatives. So if I say that f of x times g of x is just some function, 2 functions of x, and I wish to take its derivative, what does the product rule say this is? Right, so f prime times g plus f times g prime. Okay? Now, the idea is that, okay, now that we have this, we're actually going to take the antiderivative or integral of both sides. So let's do that. So we have the integral of f of x times g of x prime dx equals integral of, by product rule, f prime times g of x plus f of x times g prime of x dx. Okay? So here's what's happening with this. So what we notice with the left-hand side, well, we have the antiderivative of some expression. We'll have the antiderivative of the derivative of some expression. So what should that tell you about how this simplifies? We have an antiderivative of the derivative of some expression. So what should that tell you about how this simplifies? What's that? Yeah, they cancel out, right? So in this case, you're just left with f of x times g of x, right? So now you might think, well, wait a minute. Are we supposed to add plus c to this? Well, normally we would, but there's still these indefinite integrals here, so for now we're going to hold off on adding plus c. Okay? And then because we have a sum of 2 functions here, we're just going to go ahead and split up the integral as such. So we have the right-hand side becomes f prime times the integral of f prime times g dx plus integral of f of x times g prime of x dx. Okay? All right? And now what I'm going to do is I'm just going to subtract over a couple things to the other side and then call it good. So here's what I mean. So all I'm really going to do is I'm just going to subtract this integral over to the other side. Okay? So this becomes f of x times g of x minus integral of f prime times g of x dx. All this equals the integral of f of x times g prime of x dx. Okay? So now here's what I'm going to do. So now I'm going to let u equal f of x and v equal g of x. Okay? So then what does this get us? So we can get du and dv. So if we recall similar techniques that we've been doing with the substitution method, then if u equals f of x, then du equals what? Yeah, f prime of x, and then what else do we have to multiply by? Yeah, dx, right? Okay. And then similarly, dv would be g prime of x dx. Okay? So now, if we take this into account, we then say, all right, so f and g are right here, so we have uv minus, and then we have g of x, which is v, and then we have du, which is f prime and then dx. So du equals integral of f of x, which is u, and then g prime, which is dv. Okay? Or to switch the sides, we essentially have the integral of u dv equals uv minus integral of the du. Okay? Now this is going to be important because this guy has a specific name to it. Namely, the integration by parts formula. Okay? And one thing I would strongly make sure you do with these types of integrals is memorize them. Okay? Now you might think, well, why do I need to memorize this? It seems kind of abstract. Well, the reason why should we care is because this formula, this integration by parts formula, which I will denote as asterisk, because asterisk helps evaluate. So star evaluates some integrals. Substitution can't. Okay, so that's why we need this integration by parts formula. And to give you an example of what I mean by such a function or such an integral, let's take a look at example 1 to see what I mean. Okay, so for example 1, the premise is we have to use integration by parts to evaluate the integral of x times natural log of x dx. Okay, so the idea with by parts. So choose appropriate u and dv to get du and v, and then apply the asterisk rule that we have up here. Okay? So here's what I mean. So let's go ahead and say, all right, let's let you put u here, and then let dv go here. Okay? So if you were to take a look at this integral and sort of see how we could deconstruct it into u and dv, given what we've just established above, what would be a good choice? What do you think would be a good choice for you? Just picking an arbitrary candidate.
Natural log of x.
Okay. Yes, that will be the correct one, but let's suppose for now that someone picked x first, just for the sake of the argument. Okay. So if we were to pick x first, just by simple inspection, we think, okay, well, x is the leftmost expression, so let's try that first. Okay. Then you should be able to see pretty quickly that, well, du is dx. That's nothing too crazy there. But dv ends up becoming basically everything else, quote unquote. So dv ends up becoming natural log of x dx. But then you realize, well, wait a minute, what is v exactly? The problem, though, is that suggests we need to know the integral of natural log of x dx. But here's the problem. We don't know what this integral is doing. We don't have a nice antiderivative for this, at least not right now. So we don't know the antiderivative of natural log of x. So that means that u equals x and dv equals everything else. That's not going to work. So, whatever. All right. So here's our first try. Okay. So now let's try, as you suggested, u equals natural log and see if that gives us anything. So here's second try. So then let's try u equals natural log of x. Let's see what happens. So that way dv ends up becoming x dx. All right? So then du, well, should be what times dx? Yes, 1 over x, right? Times dx. Okay. Now, with v, again, it's going to be, you're going to need to work with the antiderivative of x times dx. So what would that be? Someone else? Antiderivative of x.
1/2 x squared.
Yeah, 1/2 x squared, right? So I'm going to write this as x squared over 2, okay? Now, you might think, well, Tim, you've been stressing adding plus c for so long, why are we not adding it here? Well, the reason is because if you notice in this integral above, we still have an indefinite integral here, right? So what we're going to do is we're going to add plus c after everything is said and done, after all the integration is done. So we'll add plus c after all integration. Okay? So don't add plus c here. Okay? Okay? So go ahead and box everything in. So now here's what happens. So now we have x times natural log of x dx. Okay? So now we just apply the formula. Now we just apply this formula here with all the things we have. So we got u, du, and v dv. Okay? So in this case we got uv, so u and v. So natural log of x times x squared over 2. Okay? And then minus integral of v times du. So we have x squared over 2 times du, which is 1 over x dx. Okay? So let's clean this up a bit. So here on the first term, we have x squared over 2 times natural log of x. Nothing we can really do with that, so leave that alone. Then you realize, all right, well, we have x squared over x, so that cleans up pretty nicely to just x over 2 dx. Right? So at the end of the day, this will simplify to what? So we have x squared over 2 times natural log of x, and then minus antiderivative of x over 2. Well, by similar reasoning as what we had over here, this would just be x squared over 4, and now you add plus c. Okay? So that will give you your antiderivative that you need. All right? So any questions on example 1? Okay. So I know this is kind of a new trick, but are we okay with this? Good? Nay? Somewhere in between? What's with a somewhere in between? You had Subway sum up. Like what was? Gotcha. Yeah, this is kind of a new technique, so yeah, it's just one of those things where you just have to get enough practice in, and then we'll be good. Okay. So now you might think, all right, well, this seems kind of crazy. How do I choose U and dV in general? So let's get into that. So if we want to choose U in general, we have to choose in this order. Okay? So how do we choose U in general? But thankfully, there's an acronym that lets us do exactly that. So let's talk about it. So this acronym is called LIATE. Okay? So liate, or however you want to pronounce this. There's not really a formal pronunciation for this, so just do whatever you want in that case. In any case, so here's what I mean. So L is for logarithms. So what I mean is that stuff like natural log of x, natural log of 3x to the 5th, natural log of 2x, or 2x, and then quantity squared, etc. Okay? So that's what I mean by logarithms. I is for inverse trig. Thankfully, though, that's not something we need to care about in this class, so you can skip that. So, not for 16020, so you can skip that. A is for algebraic. Okay? And basically, it's basically just a fancy word for polynomials in this context. So what I mean is that like polynomials like, x squared, x cubed plus 2x plus 7, etc. Okay? One thing to keep in mind, though, is that you cannot have roots here. So no roots. Okay? So that's one thing to keep in mind with this. And T is for trig. So like cosine of x, sine of 2x over 3, etc. Okay. And then E is for exponential. Okay? So stuff like e to the x, e to the negative 2x plus 1, etc. Okay? Or I'll add one more. E to the x squared, etc. Okay, there we go. So, you might think, all right, so how does that sort of tie into what we had in example 1? So, example 1, L was before A. So, choose U equals natural log of x. So dv becomes everything else. So x dx. So quote unquote everything else. Okay. So that's basically the idea of how to choose U in general. Okay. So any questions on that part? Yeah?
So if there's no roots in algebraic, where do you write it at the bottom?
Yeah, so in this case, like you're not supposed to, if you see like a cube root or a square root or something like that, that should indicate that's not what you should be choosing for U. That's all that says. And we'll see an example of that in a bit, but that's the idea. Okay. Any other questions on that? Okay. So let's apply this rule that we just established to this example here, so 2a. So evaluate the following integrals using integration by parts. So with a here, we have x times cosine of x dx. So by our acronym that we just established, so by Liate, okay, we need to choose u and dv. Okay, so by our acronym, what would be an appropriate choice for u?
Cosine of that.
Well, remember, we need to choose in this order. So in this case, which, like, the higher up we go, that means should be our choice we need. So remember, algebraic corresponds to polynomial expressions. So that can include any linear functions.
Oh, so
X, right. Okay, so u equals x, and then dv becomes everything else. So that means dv is now cosine of x. dx. So that way du, as we already saw, well, that's just dx. And then, sorry, not dv, just simply v becomes what? So here we just have to take the antiderivative of cosine of x dx. It's just sine of x. Good. Okay? All right. So then that implies that our integration by parts formula gives us the following. So x times cosine of x dx equals u times v. So x times sine of x minus the integral of v times du. So sine of x and then dx. Okay? But thankfully, this has a pretty nice integral, doesn't it? So we just have x times x times timeout. Okay, there we go. Try this again. X times sine of x minus, so we have x times sine of x, and then we have minus the integral of sine of x. So someone else, what would that be? Go ahead. Yeah, so we have minus negative cosine of x, right? Okay, and then what's the last thing we need? What's the last thing we need after every integration? Let's see. Good. Okay. So ultimately, at the end of the day, we have x times sine of x, and then plus cosine of x, plus c. Okay? And that's 2a. Okay? Okay, so any questions on 2a? All right. Okay, so that wasn't too bad. So let's make things a little bit more interesting. So now here's where things get a little more interesting. So with 2b, we have the integral of x cubed over the square root of 1 plus x squared dx. So if you were to use our rule that we've established, then what would be a good first guess? What would be a good guess for our choice of u in this case? You got a guess? Okay, we could try x cubed. So if we let u equal x cubed, that naturally means that dv needs to be everything else, right? So dv becomes, well, in this case we would have 1 plus x squared to the power of negative 1/2 dx, because you have a square root on your denominator, so this will give you negative 1/2. So thankfully we already know how to differentiate this part, no problem, but well, wait a minute, how do we integrate this guy? Don't really know how to do that, do we? So we have to be a little bit careful here. So careful. Because we know how to integrate du, no problem. That's just 3x squared dx. But we don't know how to integrate 1 plus x squared negative 1/2 dx. Or at least not with respect to the tools that we already have at our disposal. So we have to be a little bit careful with how we manipulate this. So So we can't integrate this. So instead, let's try something else. So ultimately, we will need to have x to the power of something as our u. So u equals x to the something. But how do you think we can rectify our choice of dv given the integration techniques that we know so far? So we're still going to need to we're still going to have 1 plus x squared to the negative 1/2 dx. That's much as certain. But what do you think we're going to need to multiply here to be able to work with the integration techniques that we already know? So here's a hint. So remember with the substitution technique when I said that in order to choose the appropriate substitution, you have to have the derivative of, this inner function has to be a constant multiple of something else outside inside the integral, right? So in this case, I would suggest, since 1 plus x squared's derivative is 2x, maybe try multiplying by x, seeing what that gives us. Because if we multiply by x, well, we can integrate this with substitution, can't we? So in this case, let u equal x squared because of it. So we're basically just borrowing a factor of x from x cubed here to be able to integrate dv. That's all we're doing. All right. So du, well, that's 2x dx, no problem. But then what would the antiderivative of x times 1 plus x squared to the negative 1/2 be if we utilize u substitution? Or just substitution. Give you guys a second to integrate x times 1 plus x squared to the negative 1/2. Using substitution. Go ahead. Close. It would be 1 plus x squared to what power? Yeah?
Oh, to the 1/2.
1/2 power. Good. Okay. So if you utilize u substitution or substitution integration, then this would give this should be the antiderivative you get out of this. Okay. All right. And I'm seeing some confused heads, so in this case you would have to utilize the substitution where your dummy variable corresponds to 1 plus x squared. So for instance, if you let w denote your dummy variable because u already equals something here, we have 1 plus x squared, so that way dw becomes 2x dx. So then if you integrate this, then you should end up with, well, 1/2 times w to the negative 1/2 dw. So if you take the integral of this with respect to w and then put everything back in terms of x, then this should be the thing you get out of this. Okay? So that's the idea. But in any case, let's go ahead and go back to our integral. So So if we apply the integration by parts formula, we have u times v, so we have x squared times 1 plus x squared to the positive 1/2, and then minus integral of, let's see, 1 plus x squared, so that's v, 1 plus x squared to the positive 1/2, and then times 2x dx, because that's du. Okay? So then, in this case, if we notice, well, we basically have a very similar antiderivative we got to work with here compared to our antiderivative here. So if we utilize the same tricks that we utilized in finding the antiderivative of v, or the antiderivative of this guy here, rather, then what should we get as our antiderivative of this guy in terms of x? So we're going to need to use the same dummy variable. So what would we get out of this? Go ahead. Right. So we have x squared times 1 plus x squared to the 1/2, just from this term here. And then if you apply the same dummy variable that we have over here, and work with similar substitution techniques that we had here, then you should end up with, as your antiderivative, 2/3 times x squared plus 1 to the 3/2. Okay? And then after all that, you then add plus c. Okay? Okay? And that's example 2b. Okay? So any questions on any of that? Good? Nay? Somewhere between? Okay. I'm not seeing a lot of thumbs up, so any questions on this, just before we move on? Okay. Then we shall move on. Move on we shall. So, we'll look at part 2c then. So now we have the antiderivative of natural log of 2x to the 5th, all that raised to the power of 2, and then over x squared dx. Okay? So based off of our acronym, our LIATE acronym, what would be a good choice for u and dv in this problem? And then, yeah, we're going to need squared, right? In this case, we will actually need it here. Okay? So we have natural log of 2x to the 5th, quantity squared. So that way dv becomes everything else, namely 1 over x squared dx. Okay? So here, let's see. Well, v is just the antiderivative of 1 over x squared. And you should be able to see pretty quickly that this is just negative 1 over x. Nothing too crazy with that. But then what about du? If we apply the appropriate derivative rules on this guy, then what should we get as our form of du? So it will be something times dx. Go ahead. That's part of it. 10 over x times,
dx.
well, that too, but also, remember chain rule.
20x is equal to
So let's take a look at this. I think we're a bit confused on this. So let's do a quick review. So by chain rule, we say, all right, well, this is going to be 2 times. So basically, the first part of chain rule says we have to take the derivative of the outer function composed with the inner function. So we have 2 times natural log of 2x to the 5th. Okay. And then by the chain rule, we then have to multiply by the derivative of natural log of 2x to the 5th, right? So what's the derivative of that? I think you have that. Yeah, that's just 5 over x, right? dx, okay? So if we clean this up a bit, we end up with 10 over x times natural log of 2x to the 5th dx, okay? So now we apply our good old integration by parts formula. So now we have uv, so u times v is going to be negative natural log of 2x to the 5th, all quantity squared, over x, and then minus antiderivative of negative 1 over x times 10 over x times natural log of 2x to the 5th dx. Okay? So clean this up a bit, you just have, well, these negatives cancel each other out. This can be compressed into 10 over x squared. So we have negative natural log of 2x to the 5th, quantity squared, over x, and plus 10 over x squared times natural log of 2x to the 5th dx. All right, well, so this part's fine. First term's nothing too crazy, but what do we have to do with our second term? Well, it doesn't really seem like we have any good integration techniques in regards to, lesson R, antiderivatives, or substitution techniques. So what do you think we got to do with this guy? Well, what would be our substitution though? So substitution's probably not going to work. So what's our only option left? Looks like we got to do by parts again, don't we? So just so you guys know, there will be problems where you may have to do multiple integration by parts. Integration by parts again. Okay. Okay. So, with that in mind, let's go ahead and say, all right, well, what would be our good choice of u and dv in this case? Okay? So, if we utilize similar reasoning as we did above, by which I mean this guy here, then what would be an appropriate choice for u and dv here? Yep. So yeah, nu becomes the natural log of whatever we have, and then dv becomes everything else, right? So v, well, that's just, you can see pretty quickly, this is just negative 10 over x, nothing too crazy there. And then du, well, as we already saw above, the derivative of natural log of 2x to the 5th, as we already saw above, this is just 5 over x, isn't it? So we just have 5 over x dx, so that part's there. So, with all that in mind, let's go ahead and write everything out. So we have negative, so we have the first term here, so negative natural log of 2x to the 5th, quantity squared, over x, and then, let's see, we have plus, so we would have plus let's see, u times v would be negative 10 times natural log of 2x to the fifth over x, and then minus v times du, so that would simplify pretty nicely into just negative 50 over x squared dx. Okay? So, let's see. So here we have just a negative on this term here, so not much we can do with that. And then here we just have two negatives that cancel each other out nicely. So let's see, at the end of the day, we have negative of natural log of 2x to the fifth, quantity squared over x, then minus 10 times natural log of 2x to the fifth over x. And then lastly, we then have the antiderivative of 50 over x squared, which is so what is the antiderivative of 50 over x squared? So
negative 50 over x.
yep, and then negative 50 over x. And then we're done with our integration, so now we just add plus c, and then we're done. Okay? And that's part 2c. All right. So any questions on 2c? So, yeah, like I said, this is just one of those examples that illustrates that, hey, we may need to do multiple by parts. That's all this is saying. Okay. Okay, so if there are no other questions, we'll do one last example. I know that there's two on the back, but E says time permitting, so we only got 5 minutes, so that's not going to happen. So let's move on to the last one. So the integral we have, in this case now we have a definite integral from 3 to 4 of x times x minus 3 quantity 7. Okay? So the thing is that we still apply the same rules that we've been doing even with a definite integral. So still apply our acronym, Liate acronym, even with definite integral. Okay? So first off, that should probably indicate, well, first thing we got to do is figure out, well, what's the antiderivative of this thing? So let's use our good old use our Liate acronym to determine our choice of u and dv here. So in this case, we end up having two algebraic expressions here that we can use. So what you notice is that technically you could, utilize something like, say, something like integration by substitution here, but for this purpose, let's go ahead and use by parts to see if we can get the same results that you can check with substitution. All right? So what would be an appropriate choice for u and dv? So we notice both of these are polynomial expressions, but which of these do you think would you want to let u to make things a bit easier on our Would you want to let u equal x, or would you want to let u equal x minus 3 to the 7th? We could do that, but I think for the sake of our purposes here, let's make things a bit easier and just work with u equals x. Just in case we're in the situation where, say, this ends up being something to the 7 halves instead. So that way, in case that more general situation pops up, we can be like, all right, well, let's just use u equals x instead. So then dv becomes x minus 3 to 7th dx. Okay? So du still equals dx, as before, but then with v, we have to take the antiderivative of x minus 3 to the power of 7. So in this case, if we utilize the appropriate integration techniques, in this case substitution, what would be the antiderivative of x minus 3 to the power of 7 dx? x minus 3 to the 8th all over the power of 8. Okay? So that's that. So now we have equals, we have x over, so we have u times v, so this would be x over 8 times x minus 3 to the power of 8, going from 3 to 4, minus the integral from 3 to 4 of v times du. So we have x minus 3 to the power of 8 over 8 dx. Okay? So what I'm going to do is say, all right, well, by similar reasoning as up here, we'll just go ahead and say that the antiderivative of this guy ends up being what? So borrowing this first term here, we have x over 8 times x minus 3 to the power of 8. And then minus, by similar reasoning as our integration here, you should end up with x minus 3 to the power of 9 over, in this case, 72. And the reason I have 72 here is because this is just 8 times 9. So that's how we get 72. Right? Okay? So that's how we get that. So then from here we just apply the fundamental theorem of calculus. So let x equal 4, and you should end up with, well, let's see, 4 over 8 times 4 minus 3, so that's just 1 to the power of 8. And then minus, well, let x equal 4 here, and you just end up with 1 to the power of 9 over 72. Right? And then minus, let's see, let x equal 3. Well, if you let x equal 3 here, both of these terms are just going to cancel out, so you're just left with a big fat 0. So ultimately, at the end of the day, you're just left with 4 over 8 minus 1 over 72. Okay? Now, if we were to put this all into one fraction, then what you will notice is that, all right, well, 4 over 8, if we were to put common denominators here, all we would have to do is just multiply the top and bottom here by, in this case, 9, because that'll get you the common denominator of 72. So we have 36 over 72 minus 1 over 72. So at that point, you can then just say, all right, then you should have 35 over 72 as your final answer. Okay? Okay. Any questions on any of that? All right. So yeah, like I said, we didn't have time to do part E, but I will let Pavel know and be like, hey, you guys can check it out on the webpage. Yeah?
The lesson is Wednesday, right?
Yes, Wednesday. Yeah. Okay. Any other questions? Then I'll see y'all on Wednesday covering the second by parts lesson and the next quiz. All right. See you then.